Okay. So last class, yesterday, we were looking at partial differential equations. And what we said was that so far what we have been seeing are variables where there was one independent variable and one dependent variable. But now we are relaxing that a little bit and saying that the dependent variable is now more than or is a function of more than one independent variable. And to understand partial differential equations, we are going to look at the heat diffusion equation, the wave equation, and the Laplace equation. So these are the three major equations that we are going to be using. And we're going to be looking at the method of the separation of variables as the vehicle to understand the solutions. Okay. We'll also use Laplace transform and Fourier transform methodologies. Not a whole lot, but the major problem there being that you get to some point in a very nice, neat, elegant fashion, but then when you have to invert those equations, then you start getting into trouble. So that's why we're not going to spend too much time on it, but at least we'll appreciate that sometimes solutions come very easily for certain situations. So we started by looking at the one-dimensional heat diffusion equation, and physically it is just a rod and there is some initial temperature distribution, and the ends of the rod are anchored at some temperatures, and you are supposed to find out what's going to be the distribution of temperature as time goes on. And we are not going to derive any of these equations because we are more interested in only the solution and not where they come from. And once in a while, just when some mathematical operation starts to become a little bit fuzzy, we start taking recourse to the fact that there is some kind of a physical interpretation to that equation. Otherwise, it's purely a mathematical abstraction as far as we are concerned. So this guy is an equation in second order in space and first order in time. And so you need two boundary conditions on space and one initial condition on time. And what we said was that we'll assume that the separation of variables is going to be a possible methodology. And the separation of variables, when you try to use, it's going to have the dependent variable we are going to say is going to be the product of the independent variables and product of functions which have got only the independent variables. So u here is the dependent variable, is going to be a product of x cap x of x. The capital X is a function of x only, and then a capital T of t, where the cap T is a function of t only. So these were the two variables that we had. And then it's just some brute force algebra that we need to do. And what we said was that you do the algebra and you see that this particular equation can be separated. And we said that the two sides of the equation are functions of either t only or x only. And so we are going to equate it to some constant, and all constants again are not possible. If you say 0, then it turns out that time t, cap t, comes out to be a constant, which means that the variation in little t is absent, and that's not acceptable. And if you are going to say that right hand side is minus of or plus of lambda square, then what happens is that you're going to get a solution that's going to be blowing up. So that also is not going to be a valid solution. So later today we are going to look at the x and then again show that the so-called right-hand side gets into restrictions of this particular nature. But either you use t or you use x, ultimately the conclusions should hold for the other variable. So in here we said that we would now go ahead and say that e to the power of minus lambda square t is going to be some kind of a representation for the variable cap t. And now it's time to go ahead and get the solutions for the cap x, and you need to find out the boundary conditions, if you will. And at x equal to 0 and at x equal to L, we said that the variable u is equal to 0. And from there, what you can do is to extract x of 0 equal to 0 and x of L is equal to 0. And once we have extracted that, you say that I would now like to see if something comes out of t also, and the time or the little t equal to 0 you put in, and the condition really does not give anything conclusive, so we just say that okay, we are going to take care of this headache as we move along. Alright, so we said that we have now the condition on x, so you go ahead and start trying to solve for x. So x double dot is minus lambda square x. This is something that we have seen when we were talking about the ordinary differential equations, and you know that the solution is going to be some kind of a constant times cos lambda x plus another constant times sine lambda x. Looking at the conditions on x, we said that the c is going to become 0, and the lambda, which is going to be the so-called eigenvalue, can be shown equal to n pi by L, and n can go from anywhere between 0 to a very large number. So which means that I've got multiple solutions to the problem. So which solution to choose is up to you, and it depends on the conditions that need to be satisfied by the equation. So the final solution can be written up as u equal to a sub n. The sub n refers to the nth eigenvalue, sine n pi x by L times sine pi n pi x by L e to the minus k times lambda square t. Okay. So this is the solution, and we have used up two conditions, and if you try to put in the third condition, then it turns out that it's a little bit difficult to comprehend the fact that the third condition can be right away satisfied. Okay. So the third condition getting satisfied is going to be subject to the fact that Px must be amenable to some kind of twisting, if you will. And if Px is itself sinusoidal, some kind of sine n pi by L times x, then you have a value for an, otherwise no. Okay. So, but since you already have exposure to the Fourier series, you say that Px can be represented in terms of sines, and we have seen that you can brute force make that Px into an odd function, and you can represent that as a series of sines. And on the right hand side you have got something else. So you say that let me try to see if the left hand side, which now has got a large bunch of signs, the right hand side appears to have a large bunch of signs because the n is going to be a variable. So what you hypothesize is that maybe I'm going to say that I'm going to attempt a solution that has got a sum of the solutions because my equation happens to be a linear equation. So we said that we are going to hypothesize that U is going to be summation of a large number of UNs. That's perfectly fine. We have done this n number of times in the past when we were looking at ordinary differential equations. And the original differential equation is that, and if you substitute it, I mean, you can reasonably nicely satisfy the whole thing. And when you substitute it, you get a summation, and it appears that we have made life more difficult for ourselves, but indeed it looks, or it turns out that that's not really the case. So you have summation of unx equal to 0, and that's where the 0 is very helpful, because if you have got something on the right hand side equal to 0, the left hand side has got a summation, you can say that each of those terms is going to be equated to 0, or I can do that. Okay. So all the UNs at x equal to 0 t can be equated to 0 individually, and all the UNs at x equal to LT can also be equated to 0 individually by virtue of that boundary condition there. Okay. The other condition which is there now is amenable to some kind of Fourier series. So you say that summation of UN is equal to Px, and Px now you are going to expand it as a Fourier series, and you are going to subtract each of them and say that now U's are all going to be equal to sines. Okay, so that is one approach which one can take, which is what we had done last time, was to say that Px is going to be equal to summation of Cn sine n pi x by L, and from our Fourier series analysis that we had done earlier on, you can get those Cn values, and now you have got a system that you can easily solve. Another way of looking at it would be to say that, all right, I have gotten my solution, and we have hypothesized that U is going to be equal to summation of a large number of these UNs, and now you have said that UN can individually be said that this I'm going to take, and each of those UNs, UN partial U partial T is equal to alpha square partial U partial X square for UN, because that's what this guy is letting us do. The last condition, let me just leave it alone. Okay, the last condition I'm not going to do anything, and I'm going to get my solution for all these UNs, and the eigenvalues are known to me, and at the end of the day, this condition tells me that P of x is equal to summation of all the U's, right? And you just exploit this guy, and you say that P of x is now equal to summation of all these UNs. Those UNs, they had those eigenvalues, etc. So sine of n pi x by L, and e to the power of minus lambda square alpha t, and this guy is at t equal to 0, so we can get rid of this term here. So that's what's written up there. So you have got P of x is equal to summation of an sine n pi x by L, and now can we get our ans? No Fourier series, nothing. Just brute force, we have just said that. We opened up the conditions on X, we went ahead and worked out and saw that X double prime ended up with those eigenvalues, and at the end we said this was an additional condition that needed to be satisfied, and therefore P of X is equal to this guy here. Okay, can I get an from here? This is 1 to infinity. Can I get an from there? Yeah, so what you are saying now is that, remember, these guys from your 10th class trigonometry, you know that these guys are orthogonal functions, right? That I know from my trigonometry. So all that I need to do is to multiply both sides, which is what we did for the Fourier series. Even for the Fourier series, we did the same thing. You integrate, multiply with sine m pi x by L, you integrate this guy, multiply with sine m pi x by L, and we know that when n equal to m, that term is going to survive. When m is not equal to m, that term is going to go away. Okay. So we just, for the sake of completeness, put this guy 2 by L. Remember we said that for the sines and cosines to be orthogonal, 1 by pi minus pi to pi, so, or 1 by pi 0 to 2 pi. Okay. So this is going to go from 0 to L, and then I have got my 2 by L, so I know what this an is going to be. So this equation is going to tell me what my ans are going to be. I can get my an. Either way you get the same thing. From the Fourier series, if you had expanded this as, right, sum of C sine, we called it a B, Bn sine n pi x by L is equal to Px, right? And then all of these B's we got by just doing the same thing there. So it looks as if the Fourier series helps you out here. This, however, is a slightly more desirable approach, but as of now, the two approaches appear to be the same. No advantage whether you use the Fourier series or you went ahead and said, at the end, I'm going to be using this, and then I'm going to be using this. Solution is obtained. No issues. Okay. So finally, the equation which we had somewhere there, the so-called heat diffusion equation, partial u partial t is alpha square del square u del x square. The solution to that guy is going to be that. Okay. So each of these un's we have obtained the solution. So the summation of the entire thing, that's what we had hypothesized. That's going to be the overall solution to that partial differential equation. Okay, so this was for one set of boundary conditions. Okay, so I'm saying the higher n values decay faster. I mean, that's something that you can look at the equation and say, nothing very useful in that statement, but at least if you are interested in how this u is going to decay with time, then you see that if your n is higher, because that's sitting in the square, those terms are going to be much less significant because they decay off very fast, and only the lower values or the lower eigenvalues are going to make any difference. Okay, but that's only a matter of more detail. This particular situation, we have obtained a solution by having a set of boundary conditions. Okay, my set of boundary conditions was, at the left end we made it equal to 0, right end we made it equal to 0. We are going to relax all these one by one, but as of now we had a set of boundary conditions, we had a differential equation, and for the set of boundary conditions, we were able to get a solution without much trouble, so to speak. Decent amount of algebra had to be done, but that was quite all right. You went ahead and obtained a solution. Let's take one more case, and which is similar, but it's a little more messier than this particular case. So let us say now, okay, so we had this situation, we had some kind of a domain, so this was L. So at time t equal to 0, there was some px that continues to be, okay, and at the left hand side, now we said u at 0, right, x equal to 0, and at all t, now we say that we had 0, let us say that it is equal to some constant u naught. That's a condition that has been given to me. Similarly, on the right side, we say del u del x has been given to be equal to minus of h u minus u naught. Whatever this u naught may be, it is known to me, it is a constant. Okay. So I've got a domain, this is my domain which is L, there is a funny initial condition on it, it doesn't bother us very much, and the left side is given to be a number u naught, the right side is given to be looking like so. So that's the situation that we might like to go ahead and get a solution for. Okay. The methodology remains the same, which is to use the separation of variables. We are going to use that over and over and over and over again. But every time it starts to come up with some or the other headache as we move along. Initially everything is good, then we start to end up into some kind of rough weather. Okay, so the separation of variables you will try to do, but before that, right, if you look at the previous example, remember, we had a 0 here and we had a 0 here, and we said that the zeros are helpful to us, okay? Or the so-called, if you have got homogeneous boundary conditions, they are helpful to us. Non-homogeneous boundary conditions of this nature give us trouble, so you would like to somehow homogenize the problem before you attempt a solution. So you want to make this homogeneous. So essentially what we are saying is we would like to see it 0, or homogeneous means if you put k times the variable, that will also satisfy the equation. Alright, so our conditions are u equal to u naught. So this is one of the conditions, and u at x equal to 0 all time is equal to u naught. So how do I make this guy homogeneous? This guy here homogeneous? What would be the easiest way of trying to make it homogeneous? I want to make it 0 somehow. So we change variables. What would be the strategy? I would like to get a 0 on the right hand side. I am permitted to make changes to the governing equation. What would I do? I will just say that u minus u naught, correct? This was what was there on the midsem also in some sense. So we say that u minus u naught, I am going to call it a theta, which is another variable here. Okay. So now that means that I can write my governing equation del u del t is equal to minus alpha del square u del x square. I can just go ahead and replace this guy with a theta. U minus u0, u0 is some constant, so I go ahead and do that, and then I have theta at x equal to 0 all time t is now equal to 0. Great. So this is homogeneous. Right? Now let's look at the other condition which was there, which said del u del x is h times u minus u naught. What happens to that? Del u del x becomes del theta del x, right? We are saying that theta is equal to u minus u naught. So del theta del x is del u del x. So del u del x is equal to minus h theta. Now you may say, what happens if this second fellow did not have u naught but a u1? We're going to relax that as we move along, but as of now, let us just say that the two u naughts were the same. Okay, so I've got theta x0 t equal to 0. Is this homogeneous? We are trying to make the conditions homogeneous. That makes life easier for us. Is this guy a homogeneous condition? Yes, because if I put k times this, the k cancels off, so this stays the way it is. Okay, so this is something that we need to be trying to be putting that equation in this particular form so that life is easy for us. Okay, so now we say theta is equal to f times g. F is a function of x only, g is a function of t only. Okay. Then you do the same thing which we have done for the previous case, and we are going to get f double prime by f is equal to g prime by g, and we are going to say that that is going to be equal to sum k square. Okay, sum k square. Okay. Now this could be plus or minus. Okay. So whatever that may be. In this particular case, now let us go ahead and, for the previous case, what did we do? How did we argue for a SIGN of k square? We said that this guy should not blow up, so we had used this condition here. And then I had said that it's not necessary that you use this all the time. Let us go ahead and use this guy here and see what happens. Okay. For both situations, the conclusion should come out the same. Okay. Whether you are going to use this guy or this guy to argue on the sign SIGN of this k square. So the first thing we say is, let me put k square equal to 0. Let me put k square equal to 0. So what happens to f? If k square is 0, f is equal to what? F is going to be equal to f double prime by f is equal to 0, which means you just ordinary differential equation, differentiate it 2 times, you get f is ax plus b, right? So remember, you can argue like in the earlier case and then get rid of 0. Now we are arguing using the x, that's all. This is just another way of trying to essentially get rid of my 0. Okay. So with no bias to either this or this, we would like to say that we can argue for this guy also and say that you are going to get it equal to 0. Okay. So f0 is equal to 0. This is what our that top condition is going to tell us. This guy is f times x equal to 0, g times t equal to 0. Remember, that's why we want this guy to be 0. So whatever this value of g may be, f0, so this implies f0 equal to 0. So f0 is equal to 0. So what does that mean to the constants? If f0 equal to 0, what can I say about a or b? A is 0. Okay. So this guy is going to go away. So what we are saying is that at x equal to 0, this term goes away, which means that this implies, number 1, b is equal to 0. Okay. So at x equal to 0, this term went away. So b is going to be equal to 0. So you start by saying that this is the case. Okay, what is my next condition now? Next condition is this here. Del theta del x is minus, so this is going to be f prime is minus hf. That's what that's going to be. So if this term is here, so f prime, what is f prime equal to? A. So f prime is equal to a, which is also equal to minus h times what? Ax, but this x is at x equal to L. This is at x equal to L. That's the condition that we have. Okay. So if we are going to say that, then you get A is going to be minus HAL. Let's now get rid of this. And if we say that A is not equal to 0, if A is not equal to 0, then I can divide through and I'm going to get HL is equal to minus 1. Okay. But in the original problem statement, we have said that H is some kind of a positive number, L is some kind of a positive number, so HL cannot be equal to minus 1. And so the only option for me is to have A equal to 0, and if A equal to 0, you get a trivial solution. Looks like a very roundabout saying that lambda equal to 0 does not work. You could very easily use this and get that. Okay. But doesn't matter, we need to cover all bases. So we are saying that if my lambda equal to 0, then the solution is going to end up with a trivial solution, which is not of interest to me. Okay. The next case would be where I'm going to have this as equal to plus k square, right? So what am I going to get as f? F is going to be equal to what? ODE, the first thing that we did when we were looking at ODEs. Assume f is equal to a e to the power of some kx, plug it in, you are going to get some value as, remember we said that whenever you have got this type of f double prime equal to some kind of lambda square f, we said we start with a e to the power of lambda x, and then you plug it in, you get the value for lambda square, and this is a e to the kx plus b e to the minus k. Okay. So the e to the power of lambda x, e to the minus lambda x. Okay. Okay, so that's my f now. Okay. Again, I will go ahead and do that, and I think I will use my slide. I don't want to do that. Okay, so what we say is at x equal to 0, f is equal to 0, because that was my first condition there. So at x equal to 0, f is equal to 0, which means that at x equal to 0, this is 0, so a becomes equal to minus b. And if a is equal to minus b, I can take A common and I'll put this like so. So that's using my first condition. The second condition was f prime is equal to minus hf, and there's a little bit of algebra that you need to do. F prime, if you take the derivative of this guy, this is going to give you k e to the power of kl minus k e to the kl. So this negative becomes a positive. So you've got ak e to the plus kl plus e to the power of minus kl and equal to minus of hf minus of ha e to the plus kl minus e to the minus kl. Okay. Okay, I've got that next expression, and now I'm claiming that if a is not equal to 0, then I can do this. But why is that expression not possible? Why is it not true? I've got e to the plus kl plus e to the minus kl equal to minus h by k, e to the plus kl minus e to the minus kl. And we are claiming that that is just not possible. Why would that be the case? Yeah, so that's the thing, okay? Because we have said that k is a positive number, and so you are going to get or whatever. So e to the power of plus kl, e to the minus kl, that's a positive number. Plus kl minus kl, that's also a positive number. H is positive, k is positive, and therefore this expression cannot be true unless a is equal to 0. Once again, a very, very roundabout way of saying that lambda equal to plus k square does not work. Okay. So if you had used this expression, it was very straightforward. So we said that the solution cannot blow up, and therefore the plus k square was gone. Okay. So finally, what remains is the minus k square, and that's the solution of interest for us. So what we say is f double prime is equal to minus k square, and you are going to get your sines and cosines now. F becomes equal to a cos kx plus b sin kx. F0 equal to 0, which means which term is going to go to 0? This term is going to go to 0. Right? F0 equal to 0 implies a equal to 0, and therefore f is again our friend sine of kx. Okay, but up to now things have all been pretty much the same. We've just been doing algebra and nothing else. Okay. Now let us see what the other condition was. F prime is equal to minus hf. Okay. So f prime is equal to what now? What is f prime? F prime, this is b sine kx. So f prime becomes equal to b times k cos kx at x equal to L is equal to what? Minus hf. So that is minus h times b sine kx. Okay. Again, we are just doing algebra. Okay. So f prime is equal to this. So b is not equal to 0. What happens if b is 0? I'm just happily dividing b on both sides, claiming it is not 0. But can it be 0? Go even one step higher. My solution was what? F was a cos plus b sine, right? So if A was already 0, B is already 0, I have nothing, F equal to 0, right? So I don't have a solution, okay? Okay, so B equal to 0 is not a valid value for that. So B is non-zero, so we are deleting that. And now what we are saying is K by H minus K by H is equal to tan KL. Okay. So this is what I got. Okay. If I used my other condition, okay. What uses that equation? What am I looking for? I'm looking for my solution, and my solution was F was equal to sine of Kx. That was my solution, right? So we are trying to solve this equation. We got up to here by using the first condition. We used the second condition and we got here. What is this condition going to tell me? Or is it going to give me anything? Is K, yeah? It's going to give me K, right? This is one equation and one unknown. We know what is H, we know what is L. K is the only unknown in this equation, right? So you can get your value for K. Okay, now this is not that straightforward, just like whatever we do. So you can go ahead and use some kind of a graphical method, or nowadays you can use some kind of a software to get the different values of K. Okay. So what I've done there is to say that I'm just plotting this function and this function, and then the intersection points are going to give me what is going to be this K. Okay. So this is just to get you now the values of K, and you can go ahead and use any method. This one is just illustrating that you get different values of K. That's what this function is going to do for you. Now, okay, fine. We got our different values of K. Now what do we do? Okay. Now we got different values of K. What are these Ks? What is K? What are these Ks? These are the eigenvalues. Okay. So I have got a whole bunch of Ks now. K1, K2, K3, etc. Okay. So those are my eigenvalues. Okay. Okay, so now what we do is we come back here. Okay, what are my eigenfunctions? What are the eigenfunctions? If I put different values of K, I'm going to get different values for this F, right? So these are my eigenfunctions, which are sine of Kx. Just like in the previous case, we had sine of n pi by lambda, and we said that you change this n and you got different eigenfunctions. So the eigenfunctions have remained the same in both the problems. Okay, it's only that the value has changed. This K has changed. Okay. So how do I proceed now? The procedure remains the same. We did everything that was to be done, and then we got this, and getting that F is not a big deal. So what we say is my final condition which was there, Px is going to be equal to summation of Bn sine of Kmx. At e to the power of minus lambda square t is equal to 1. So this was my last condition that I would like to satisfy. Now what? How do I get these Bn's? 1 to infinity. Previously, what did we have? Previously also we had Bn sine of, previously there was a Px and this was some An sine n pi x by n. Okay. And what did we do to get the Ans? We multiplied by sine m pi x by L and then we obtained the values of An, or we expanded this guy in terms of the sines and cosines of orthogonal, okay, which were orthogonal. The sines and cosines are orthogonal when this guy is a constant, right? Some constant value, integer value. Okay, now can I use the same thing here? Or can I not? Why don't I just say multiply this by sine kn x, multiply this by sine kn x, integrate, and will I get my Bn? Will I get my Bn? No, you will not. Okay, that's why we are doing this whole business here. Okay, why will we not get it? These need not be integers. Correct. They are actually not integers, which means that, remember the Fourier series when we talked about, we said that those were basis functions because they were orthogonal. Okay. They were normal, that was a convenience. But orthogonality is what you are going to be using here. So if Km and Kn are not integers, I can't do much. Okay. I'm anyway brute force doing it. I'm just saying you believe me and go ahead and get the Bn. Okay. But then, before we go ahead and say that this is going to be valid, we say that there is something else that we are needing before we can go ahead and do this. I'm doing this, right? And I'm putting certain things in red here. This still is going to be orthogonal, correct? This still is orthogonal. This works only if, in brackets, because the eigenfunctions are orthogonal since the differential equation is in the SL form. Okay. So what is this SL business here? So if the differential equation that we have talked about is in the so-called Sturm-Liouville system or equivalent to some kind of a Sturm-Liouville system, then you can show that this function and this function are going to be orthogonal. Otherwise, no. Okay. So the reason for doing all this algebra is for us to appreciate that just because some kind of a sine kx and kmx, knx are eigenfunctions, they are not necessarily orthogonal, and you have to show that they are orthogonal, and there is a means to find out whether they are orthogonal or not. If they are orthogonal, it's a happy situation. You can just go ahead and do this. Okay, so that's why that's been put in red there. Km and Kn are not integers, which means that the trig function orthogonality need not necessarily hold. Okay, the trig function orthogonality may hold, but it holds under certain conditions, and that brings us to the next topic. Not exactly the next topic, the next subtopic, if you will, where we are going to see that these functions, if they are going to be some kind of a amenable to certain particular form, then we can claim that they are going to be orthogonal. Okay. Because if they are not orthogonal, very difficult for us to do anything, or very difficult to get a solution. Okay, so, sorry, yeah, I'll correct that. Okay, and that should, in the denominator also, it should be sine k square, sine square, right? When km equal to kn, right? So, once again, since you have pointed this out, okay, the functions are orthogonal, but they are not necessarily orthonormal. That's why the denominator is there. Okay. Otherwise, we know that when km or when m not equal to n, sine square 0 to L 2 by L was equal to unity, right? So that is not necessarily going to hold here. That's why you see that bearish looking denominator. Thank you. Okay. Okay. So let us go ahead and get started on this so-called Sturm-Liouville system. Okay. So we need to look at the Sturm-Liouville system so that we can appreciate why is it that we have been able to use that orthogonality for those particular eigenfunctions and eigenvalues. Okay, before that, again, a couple of definitions. Okay, so the inner product of f and g we had said was f g dx. Okay, this was something that we had said, and when we were looking at the 2 pi periodic space, we said that this was minus L to L 1 by 2L or 1 by L, depending on whether we were in the complex domain or on the trig domain. Okay, but here we are going to define it as just integral of f times g with some limits. Remember, you make a definition and then you have to stick to the definition. Okay. All right. Now another thing is, we will try to say that some operators are so-called self-adjoint if certain conditions hold, and this self-adjoint business is something that is very useful to us. So if we are saying that I have got an operator which is L, okay, and I've got a function f, LFG, the inner product, if it is equal to LGF, then this is a self-adjoint operator. Okay, and the definition of my inner product, but again, the boundary conditions also have to be amenable. Okay. So it's not that because when we are performing that integration, it's going from A to B, and remember in the previous case also there was a minus pi to pi, etc., etc. So this guy is going from A to B. So LFG, so we'll take an example so that we see that sometimes what happens is that a particular operator is self-adjoint under certain conditions and it is not self-adjoint in some other conditions. Okay, so the same operator. So we look at a simple operator, L is d square dx square. This is an operator, and let us just say that I have got two functions, f of a equal to f of b equal to 0 and g of a equal to g of b equal to 0. Okay. So we are just looking at a self-adjoint, or we have an operator which is d square dx square, and we are trying to figure out whether that is self-adjoint given the conditions that have been given to us. Okay, so sorry, yeah, so fa equal to fb. Okay. We stop here today. I'll see you again on Thursday. Thank you very much.